Okay, hello everyone. Okay, this video is going to show you the shear stress calculation on torsional load member. Okay, in this problem we have a different kind of bar or different kind of cylinder bar. Okay, and so here's the problem description. Is that is a shaft. Okay, here's the shaft. And okay, the shaft kind of different. The shaft and A B section of the shaft is hollow. Okay, it's hollow. Again, the B C section of the shaft is solid. Okay, and he said determine the max shear stress in the shaft, and the shaft has outer diameter 80 meter, and the thickness of the wall of the hollow segment is 10 millimeter. Yeah, I think that sometimes you haven't read the description. Uh, I think I think maybe you don't know what this means, so I really need to explain this. Okay, so this is so it's a shear stress calculation. So for the shear stress for the torsional load member, the shear stress, the formula for a shear stress calculation is I think it's equal to TC. Oh, sorry. TC T rho over J. Okay, T is the torque, and rho is the distance from the center, and J is the polar moment of inertia. Okay, and then he said this problem wants you determine the maximum shear stress in the shaft. Actually, previously we say the maximum shear stress is always on the surface. Okay, all the surface. That means this rho is the radius of the rod. Okay, that means your rho is equal to the radius. But in this textbook, we always use a c for radius. Very strange. Okay, so 就是 r as a radius of the bar. Okay, but the maximum shear stress always on the surface. So I remember I draw a graph like this. Okay, so if this is a cross section of the cylinder, and here is a shear maximum. This is a shear maximum, and it's grow linearly along the radius direction. So it grow linearly. So the maximum shear stress only stay on the surface. Okay, and so here, so how to calculate shear stress on this bar? Is it to the maximum shear stress? And this shear stress we have two sections, AB section and BC section. Why? Because AB section is a hollow and BC section is solid. Okay, so because this is hollow, and this is a solid, so this implies that the polar moment of inertia is not equal. Okay, JAB is not equal to JBC. Okay, and what is the polar moment of inertia? Do you remember the formula? Is pi over 2 uh and outer radius power 4 minus inner radius power 4. That's for radius. But if the problem give you a diameter, okay, so um, it will become pi over 32 outer diameter power 4 minus inner diameter power 4. Okay, that's a formula for polar moment of inertia. Okay, so we have known. Okay, I think we need we have to use the radius. Okay, and then we have the formula for calculate the polar moment of inertia, and we have the outer radius and inner radius. Okay, for the BC section. Okay, for the JBC. Okay, maybe we just calculate the JBC and JAB quickly. Okay, so for the JAB, okay, for JAB, let's see. This problem give a diameter, okay, diameter. So looks like this formula is better to use, okay, diameter. But for don't be careful for its unit. It's 80 times 10 to the power minus 3 power 4 and minus. Yeah, what's the inner for the JB section? What is the inner radius? So we need to know this. We need to go back to this problem description. You see the thickness of the wall of the hollow segment is 10 millimeter. Yeah, this what does this mean? So I think I need to use the graph to do this translation. So it's just like this. Okay, so for AB section, this is for AB section. AB section. Okay, this is hollow. So okay, maybe it's not perfect circle, but you understand it. So this the diameter is 80 millimeter, and they say the wall of the hollow segment is 10 millimeter. So okay, let me check. The wall of hollow segment. Let me see. Let me see what is A B D. There's 60. Mm-hmm. Okay, so the problem he said the wall of the hollow segment is 10 millimeter. He said this here is 10 millimeter. The wall of the hollow segment is 10 millimeter. So it means 10 millimeter is here. Okay, 10 millimeter is here. Yeah, yeah, yeah. This description is not that straightforward. Okay, so I draw this picture for you. So, okay, so let's tell you inner radius is 60 millimeter. Okay, so it's 60 millimeter. So 60 millimeter. Okay, and 60 millimeter and to the power 4. Okay, so do I have to calculate the value first value now? Okay, no, it will we'll just keep it. Okay, so and for the okay, so for the BC section, let me see for the BC section. For the BC section, okay, BC section, yes, give you a diameter is solid, and this section is solid. So there is, if it is solid, so there is no inner radius or inner diameter. So it just use pi over 32 and 80 times to 10 to the power minus 3 power 4. Okay, that's JAB and JBC. And we use the row, we all use the same thing because at the surface, so I think row is 80 times 10 to the power 3. Sorry, so it's radius, be careful. It's 40 times 10 to the power 3 millimeter. So millimeter. Okay, okay. All right, so the next thing we don't know is the torque, the torque between the AB section and BC section. Okay, and this bar is subject to two external torque. Okay, external torque here. So okay, so what's the torque on the AB section and torque at BC section? Yeah. Once again, if I don't know the direction of a torque, for example, I just there's a torque AB, where is a torque BC? Okay, if I don't know the direction of a torque, I just assume every torque is counterclockwise. Just assume everything is positive. Okay. Okay, so and then how to solve the TAB and TBC? TAB and TBC, and then if we have TAB and TBC, we can calculate the shear stress at AB section and shear stress at the BC section on the cross section area of the rod, the bar. Okay, yeah. So the next thing is we have to solve TAB and TBC. So how to do that? Yeah, once again, cross section method. Yeah, if I under multiple external torque, and and you want to compute the torque of each section, you need to use cross section method. So I cross section here, and cross section here. Okay, so let's start to do the section analysis. So for first part, okay, first part is here. Okay, first part is here. First part is here, and external torque at A is 2 kilonewton per meter. And for TAB, I don't know the direction of the TAB, so I just assume it's TAB. I just assume it's counterclockwise. Okay, here is the first section, and I draw the other section. And I draw the finishing all section first. Okay, this section. Okay, so this Uh, okay. This is A. This is B. B is here. A is here. It's 2 kilonewton times meter. Is here is 4 kilonewton times meter. And for this problem, we calculate from the right to the left. Okay, yeah, because I think it's easy because more this the information, more many information is from is at the right, so we calculate from the right. Okay, that's much easier. You calculate from the left, that doesn't look like easy. Okay, so we calculate from the right. Okay, so I and the same thing. I don't know the direction, the torque, direction of the torque BC, so I just assume it's positive. Okay, and then we do the balance. Okay, and we do the moment balance or torque balance on each section. Okay, so we have TAB positive, and this torque is counterclockwise, so it's positive and equal to 0. And we have a TAB equal to -2, but be careful for the unit. Okay. And for TBC here, okay, so TBC plus 4 plus 2 equal to 0. So TBC equal to -6, but don't be careful for the unit. Okay, so we have TAB and TBC. Okay, it's -2, and this also TAB is -2, and TBC is -6. Okay, so that's mean because initially we assume it's counterclockwise, but we both get a negative answer. So the real direction is TBC is TBC is TABC and TAB are all clockwise. All right, it's counterclockwise and or clockwise. Okay, okay. The real direction is clockwise. Okay, the real direction is clockwise. Okay. But I think the direction doesn't affect the answer in this problem. Okay, so we have the TAB and TBC. So we have everything. We have everything. Okay, we have everything. We can calculate shear stress. Okay, so I don't have any space right now. So where should I have to erase something? Okay, so I erase erase everything here. I erase here. So let's calculate the shear stress at AB section first. Okay, shear stress at AB section. Okay, and we need to know the magnitude of the magnitude of T. We need to know TAB, and the radius is 40. Yeah, be careful. Its radius is 40 because at the surface, so it's equal to r. Okay, rho equal to r radius times 10 to the power minus 3 and divided by the polar moment of area of the AB section. So the AB section, yeah, we just calculate this. Yeah, we didn't give the numbers, but we can just copy this. Yeah. Okay, so maybe I need to also erase this. Give me more space. More space, more space, more space, more space, more. Oh, ah, ah. Okay, so 60 times 10 to the power minus 3, 4. Okay, so and what's our talk at AB? Yeah, I think he wanted us to calculate the maximum. So actually, we don't really need the direction information. So he was only want this problem also want us to determine the maximum value. So the direction is not that important. So I just put 2 in there. So I just put 2 here. Okay, and be careful for the unit because I want everything in Newton and meters. So so it's 2 times 10 to the power 3. Be careful for the unit. Okay, so after the calculation, I think you will get the answer. Yep, Yeah. So let me just give you the answer directly. I think after you putting everything in your calculator, it will give you the answer 29.12 megapascal. Okay, so that's the maximum shear stress in AB. Okay, maximum shear stress in AB section. But what about maximum shear stress in BC? Yeah, you want to determine the maximum shear stress, we only calculate AB section, but there's a BC section, right? Okay, so the BC section. Okay, the BC section. Okay, how do we do? Okay, first of all, let's just put a torque into the equation. Yeah, just the same as I did in the sigma AB shear stress calculation. I think this problem direction is not that important, so I just put the six in there. And six, and be careful, is kilonewton times meters, and I want everything in Newton times meters. So if I will put a six times 10 to the power three. 6 times 10 to the power 3. And we are saying the maximum shear stress is at the surface. So we put the radius in there. And then finally, we put the polar moment of inertia of BC section into the formula. And we just here is JBC. So it's pi over 32 80 times power 4. Okay, so and then I can erase this. No. Okay, just keep there. Okay, so after you put everything in your calculator, I think this will give you the 59.17 mega per. Okay, it's 59.17 mega per. Okay, so the maximum shear is I think it's on the B is this value 59.17 mega. So let's calculate for shear stress on the in the torsional loaded member. Okay, and in this problem, yeah, this bar is subject to multiple torque, so you need to use the cross section method to calculate the torque of each section. And most importantly, each section you have a different polar moment of inertia because this is solid, this section is solid, and this section is a hollow, so they must have different polar moment of inertia. So you must be careful, okay, and calculate each polar moment of inertia of each section. Okay, and that's it. And it's not that difficult question. Okay, and be careful for and also the concept. The maximum shear stress is always at the surface. So we put the rho equal to the radius to the calculation. So be careful for this. Okay, maximum shear stress is on the surface. Okay, maximum shear stress is on the surface. Okay. So I just finished this demonstration here. So I will see you in the next video. Okay, bye bye.